Alright, so I'll be talking about joint work with Sebastian Bubeck and Jerry Lee on the role of entanglement in designing optimal quantum property testers. Alright, so let me just start with a roadmap for this talk. So I'll begin with a crash course on quantum property testing before proceeding to an overview of prior work and our results. I'll then describe our lower bound construction and then give a flavor of the proof before concluding with open questions. Okay, so first let's just nail down the kinds of objects we'll be considering in this work. So recall, a classical distribution, right, we all know, is just some distribution over d elements, which is specified by a vector of marginals p, which lives in the simplex. Right, so the entries of p are non-negative and sum to 1. And the way in which the tester interacts with the distribution is via samples. So we can think of a sample as some kind of measurement of the underlying distribution in the form of some index from 1 to d, where the probability of that particular index corresponds to the particular entry of the vector of marginals p. Okay, so what's the quantum analog of this? So this is what's called a mixed state, and it's given by a so-called density matrix, rho. So a density matrix is some Hermitian matrix, d by d, with complex entries, which lives in the spectrohedron. That is, the collection of all density matrices which are PSD and trace 1. So what is the quantum notion of measurement? This is a bit complicated. So to measure a mixed state, there's actually an extra degree of freedom where you can specify the kind of measurement that you make. So unlike classical distributions where I only have the ability to get a random sample from my distribution, for a quantum state I can specify the actual matrices that I use to measure them with. So in particular, to measure once, I need to specify some collection of PSD matrices, which sum up to the identity. And such a collection, M1 to M little m, is what's called a positive operator valued measurement, or a POVM. And the outcome of measuring rho using this POVM is that we get some index x from 1 to little m with probability equal to the trace inner product of m sub x and rho. Okay, so some sanity checks. For one, these probabilities of measurements are all non-negative because the trace inner product of two PSD matrices is always non-negative. And furthermore, these q sub x's will sum to 1. And the reason is that the m sub x's are a partition of the identity. Okay, so the q sub x's altogether for marginals for a bona fide classical probability distribution. And in particular, this formalism of measuring quantum states subsumes classical distribution sampling. Okay, so given a classical distribution P, we can consider the mixed state, which is just the diagonal matrix given by entries of P. And if we measure in the standard basis, so if we use the POVM given by projections to the standard basis vectors, then you'll see that the probabilities q sub 1 through q sub d are exactly equal to the marginals p sub 1 to p sub d. So this recovers classical sampling. Okay, so in distribution testing, we need some notion of closeness between distributions, and typically we work with something like TV distance. And the question is, how do we measure closeness of two mixed states? And so the natural notion of distance is so-called trace distance, and one should think of this as a generalization of L1 distance, where we now compute the L1 distance between the vector of singular values of the difference. Okay, so this is in other words the Sitan 1 norm. Okay, so now let's just recall the setup of classical distribution testing. The point is that given some collection of samples from the unknown distribution, we'd like to deduce some property of P. These properties could be something like testing whether P is the uniform distribution, or epsilon far from it in TV, or testing whether it's equal to some particular distribution or far from that distribution. Okay, there are a variety of other interesting variants, but we'll really focus on uniformity and identity testing in this work. And the punchline in the distribution testing literature is that you can typically do this in much fewer samples than it takes to actually fully learn the entire distribution. Okay. Right, so in quantum world, now instead of giving samples from the distribution to work with, our model is going to give us access to some copies of the unknown state rho that we want to measure in order to deduce some property of rho. So the analog of uniformity testing is what's called mixedness testing. And here the goal is to test if rho is equal to a particular state, namely the maximally mixed state, which is equal to the identity divided by d. Or alternatively, whether it's epsilon far and trace distance. The analog of identity testing is what's called state certification. Namely, given some prescribed state gamma, I'd like to test whether rho equals gamma or is epsilon far and trace norm. And again, the goal is to do this in much fewer copies than it takes to actually fully learn the underlying state rho. Okay, so the fact that it takes d squared over epsilon squared copies to fully learn rho is a highly non-trivial fact. This was shown in recent work by Ha et al. And O'Donnell and Wright. Okay, so why do we care about this question? From a mathematical standpoint, it's interesting for being, the natural non-commutative analog of distribution testing. And from a practical standpoint, this is a necessary primitive for verifying the results of various quantum experiments in the lab, right? So if we claim that a particular experimental setup yields some quantum state, it's really, the first step you need to do is make sure that the quantum state that you get out of this process is actually equal to the one that you want it to, or is close to some family of states that satisfy some property. Okay, so it's the most basic kind of primitive that you would need in these kinds of setups. Another interesting facet of quantum distribution testing, quantum property testing, is this sort of built-in notion of adaptivity that we see in this setup and not in sort of vanilla distribution testing. Okay, so the key difference is that at every step we can actually vary the way in which we measure the distribution, whereas with classical distributions, we're just seeing a bunch of samples, and that's the only way in which we interact with the distribution. Okay. And so the most basic way that you can interact with the distribution, or the density matrix, is to fix some collection of POVMs at the very beginning, and then carry out your measurements. Okay. So this is what we call a non-adaptive form of measurement. You could be slightly more clever, and instead of picking the POVMs at the very beginning, you could choose them in an adaptive fashion. So maybe I measure the first copy with some choice of POVM, and then based on the outcome of that measurement, I pick the next POVM to measure with, etc. And we're going to call these unentangled measurements for the reason that you can actually do much more than what I've described in this current slide. So you can also view the collection of capital N copies of rho as itself just a larger mixed state in this tensored space. So you can think of rho to the tensor power n as just a d to the capital N by d to the capital N matrix. Right? And so you could just as easily design POVMs which live in this bigger space. And now instead of applying, a POVM for every copy, let's just apply this gigantic POVM to the joined state. This kind of measurement is what we call an entangled measurement. And it's not hard to show that entangled measurements can be used to implement adaptive measurements. And obviously adaptive measurements are at least as powerful as non-adaptive measurements. And the guiding question behind this work is whether we can show strict separations between these families of measurements. Okay, so now let me turn to prior work and our results. Right, so the best known results in this line of work on quantum property testing all use entangled measurements. So O'Donnell and Wright, a few years back, showed that for the problem of mixedness testing, the optimal rate is linear in D, and you can get this using entangled measurements. Okay, so the intuition for linear in D is that there are roughly d squared parameters in a density matrix, which is d by d. And just as with uniformity testing, we get this square root improvement from d to root d. Here we get a square root improvement from d squared to d when it comes to mixed-in testing. And then recently, Badescu et al. Refined this result to give an algorithm for the more general problem of quantum state certification. In terms of non-entangled measurements, the state-of-the-art essentially learns the full density matrix and takes cubic in dimension time. So why would one possibly care about non-entangled measurements for quantum property testing or learning? The main issue is that entangled measurements incur this prohibitive cost in terms of memory overhead. So you really need to simultaneously maintain all n copies of rho, and this is a bit outside of this is actually substantially outside of what we could achieve in practice right now. On the other hand, unentangled measurements, by definition, can be performed in a streaming fashion, and you only need one copy of row at a time to be prepared. And this is much closer to the sort of things that we can actually achieve in practice in the lab. Okay, so if we turn now to the guiding question behind the title of this talk, is entanglement necessary for optimal quantum property testing? Well, we can phrase this in a more formal language now. The question is, can we test mixing this with linear in D over epsilon squared copies using only adaptive or non-adaptive unentangled measurements? And the answer that we give in this work is, unfortunately, no. There is actually a strict separation between the power of entangled measurements versus unentangled measurements. Right, so the first result we show is that if you work with the weakest model, just non-adaptive measurements, you really do need this extra root D factor. So we show that there's both an algorithm that gets D to the 3 halves, as well as a lower bound showing this is necessary. And then for adaptive measurements, we show that a qualitatively similar lower bound happens. So we show that if you only use adaptive measurements, you still need at least D to the 4/3 copies. Okay, so this answers a question of John Wright from his PhD thesis. And note that because state certification is a strictly more general problem than mixedness testing, the lower bound also applies to state certification. And let me emphasize this is the first separation between entangled and general adaptive measurements for any quantum testing or learning problem. Okay, so in the remaining time, let me describe the lower bound construction before going into a sort of overview of the techniques. So the starting point for the lower bound construction is just PANINSKI'S classical lower bound for uniformity testing. So recall that he showed that you need at least root D over epsilon squared samples to test whether your samples come from a uniform distribution or epsilon far from it. And roughly speaking, he shows an impossibility result for the following hypothesis testing question. Given capital N draws, tell me whether the distribution is uniform or a random perturbation of the uniform distribution. So let me clarify what I mean by random perturbation. So let's just say the domain is even. Okay, we're going to pair up the domain into D over 2 buckets. So I'm going to pair up the first and second element, the third and fourth element, etc. And for each one of these D over 2 buckets, I'm going to pick a random bit, either -1 or 1. I'm going to design a distribution P sub z as follows. So here we see a histogram for one such P sub z where the z is given on the bottom. Right? Basically the construction says that either, for a particular index I, zi is +1, in which case we make the first bar in the bucket bigger than the second, or vice versa. Okay, so this is this famous PANINSKI distribution. And what he showed is that for this particular instance, if you have 2 cube samples, then it's hard for you to distinguish, just in an information theoretic sense, between whether your samples came from the uniform distribution or whether they came from a random PANINSKI instance. Right, so you should think of B as really a mixture of product distributions. And at a high level, the proof proceeds by passing from TV to chi-square divergence. Chi-square divergence is easier to work with because it's just some expectation of a polynomial. You get a lot of nice cancellations, and because B is a mixture of product measures, the calculation works out nicely. Okay? And so the driving question behind the analysis is, can we lift this kind of calculation to the quantum setting? There's a very natural sort of quantum analog of the PANINSKI instance, which is that you take a PANINSKI instance and you embed it into the diagonal of a mixed state, and then simply randomly rotate that mixed state. Right, so in linear algebra terms, it's nothing more than the following matrix. So define rho sub u to be, you take the diagonal matrix with entries given by P sub z for some arbitrary z, and then you conjugate it by some u chosen from the unitary group, which is Haar random. Okay, so what we want to show in our analysis is that the following TV bound holds as long as the number of copies is small. The TV between the distribution over your measurement outcomes, given that you were measuring the maximally mixed state all along, and the distribution over measurement outcomes, given that you are measuring some random row sub u all along, is small. Right, so that's our goal. And the point is that when the measurements are non-adaptive, B is yet again just some mixture of product distributions, an infinite mixture in fact, because you're varying the latent variable capital U. And in this case, you can just emulate PANINSKI'S proof, and everything works out nicely. And really, the technical challenge is to understand this adaptive setting, in which case this chi-squared no longer has a nice form because capital B isn't a mixture of product distributions. Okay, and so the key technical innovation of this work is to go about this using the chain rule. And this is, in some sense, the way in which we break the power of adaptivity. Okay, so let me now describe this calculation. Okay, so to use the chain rule, obviously we're going to have to go through some notion of distance which satisfies the chain rule. So we're going to work with actually KL instead of chi-squared. So recall KL and chi-squared are defined as follows. And so let's dive into the chain rule calculation. Okay, so the first step is where we use the chain rule. We're going to upper bound not the TV but the KL by PANINSKI'S. And to compute the KL, we're going to split it up into the sum of conditional KL divergences. Okay, so this sum ranges over the capital N copies. And each summand, we take an expectation over the transcript of measurement outcomes we've seen previously. So all measurement outcomes from 1 to t minus 1 with respect to the alternative hypothesis. So recall P sub 1 is the hypothesis in which the underlying state is not the maximally mixed state. And P1 to the negative t is just our way of saying the distribution over measurement outcomes 1 through t minus 1, given that you're in this situation. All right, this is the conditional KL divergence between the conditional distribution on the tth outcome, given what we've seen so far, this transcript x less than t. All right, so the KL divergence between this and the uniform distribution, which is essentially the conditional distribution on the tth outcome if we were measuring the maximally mixed state. Okay. All right, so this is just a step of using the chain rule. Now let me pass from KL to chi-squared just by Taylor expansion. And then skipping a bunch of calculations that don't leverage the structure of the problem, what we end up with is the following quantity. So again, we have an expectation over transcripts x less than t, but now over the null distribution, right, which is just a product distribution in the non-adaptive case as opposed to a mixture. Right? And we get this likelihood ratio quantity together with this expectation over independent unitary matrices u and u prime of this phi quantity and this psi quantity. So I won't define what the phi and psi are, but at a high level, the psi quantity satisfies the following identity, namely the expectation of psi is the square likelihood ratio between P1 and P0 over the transcripts. On the other hand, this phi quantity at a high level measures how much a single measurement can actually help you distinguish between elements of the mixture. All right, so how do we upper bound this quantity? I'll show on the next slide that you just need to show that this phi quantity is very small with high probability. All right, this makes sense because this phi quantity is just the power of a single measurement for distinguishing between rho u and rho u prime. So it should tell us very little on average over u and u prime. And indeed what we show, and this is sort of the key technical step of our paper, is that this phi quantity actually concentrates quite well. And in particular, it concentrates with roughly epsilon squared over d to the 3/2 fluctuations, which explains the sample complexity we expect in the non-adaptive case. Okay, so let's say for the time being that instead of having tails, we even have a deterministic bound on phi. So what happens then? Here's the expression from the previous slide. We can now pass the phi outside, replacing it with an epsilon squared over d to the 3/2. And now recall that this psi quantity is just a square likelihood ratio on average. And so this quantity just becomes the likelihood ratio between P1 and P0 over the first t minus 1 outcomes. And then the expectation of a likelihood ratio is just 1, and there are capital N summands. And so altogether we get that if n is little o of d to the 3/2 over epsilon squared, then KL is little o of 1. But this actually yields a stronger lower bound than what we claimed. And the reason is that we don't actually have such deterministic bounds on phi. In fact, phi could be as large as epsilon squared. And dealing with these tails is why we lose and only get this d to the 4/3. At a high level, we need to do some kind of balancing, and it's a great question to try to improve this lower bound to d to the 3/2 by avoiding this sort of balancing. All right, so finally, let me conclude with some open questions. All right, so the most salient of which is to close this gap between 3/2 and 4/3 for adaptive measurements. Some other interesting questions are, can we establish some kind of hierarchy in terms of quantum memory, where as we increase the amount of entanglement we get access to, can we actually interpolate smoothly between the d copy complexity that you get with fully entangled measurements and the d to the 3/2 copy complexity you get in the non-adaptive case. Other questions are, for state certification, can we consider more structured instances than just the maximally mixed state? Maybe we want to test identity to some low rank matrix. And more generally, it would be very interesting to see whether this chain rule framework that we've designed in this work can be used to prove both other adaptive quantum learning and testing lower bounds, and maybe even go beyond the quantum setting. Right, so that's all I have for this talk. Please ask me questions in the comments to this video, but for now, thanks.